This is the back page of 11.7 Notes, Day 2. So we're going to look at some special products today. So the first one we're going to look at is a difference of two squares pattern. And something that you need to remember is this pattern only works for a difference, meaning you're subtracting two perfect squares. So just a reminder, a perfect square means you can multiply the number by itself. So for example, 9 is a perfect square because it's 3 times 3. X squared is also a perfect square because it would be x times x. Okay, now this does not work for sums. So remember, sums means that it's adding. If it's a perfect square plus a perfect square, this does not factor. So let's look at a problem. Number 1, look at something very small. Y squared minus 9. Now, y squared is a perfect square because it's y times y, and the coefficient is 1, and 1 is a perfect square. It's 1 times 1. Okay, now 9 is a perfect square, 3 times 3. So when we go to factor this, in our parentheses here, we're simply going to write y times y, and in order to get this minus, we have to do plus and minus, and then 3 times 3. Because when I multiply this out, I get positive 3y minus 3y, which equals 0. And that's what this middle term for this binomial actually is. It's y squared plus 0y minus 9. But we don't write the 0y. That's why it's a binomial, just y squared minus 9. So I want to let you see what this looks like on the algebra tiles. So if we were to draw the perfect square in here, think about what we did in the last few days. We would have an x squared right there, and then we would have 9, 1, 2, 3, 9 little negative squares here. Okay, so in order to get these missing factors, we have these 0 pairs. So we would have maybe a negative 1 here, a negative 1x here, and a negative x here. Meanwhile, we'd have to have a positive x here, a positive x here, and a positive x here. So these would end up being 1 0 pair, 2 0 pairs, and 3 0 pairs. So when you combine those up, they equal 0. And you're left with x squared minus 9. And that factors so that you have 1x here, 1, 2, 3 negatives, and then you have an x here, and 1, 2, 3 positives. So you have to keep in your mind that when you're factoring a squared minus b squared, the middle term is 0. So you're trying to find what's going to add up to 0. Or you can just know the pattern, which would be the easier way to do this. So looking at number 2, we're going to factor a little more complicated expression, 4x squared minus 25. So we still start by looking for the greatest common factor. So 4 and 25 have no common factors. But I know that 4 is a perfect square of 2 times 2. And 25 is a perfect square of 5 times 5. So this means that this is going to factor into 2x times 2x. This is actually the second sign, the sign on the constant, which means it's plus and minus, and then 5 and 5. And notice when we check it back, we have 10x minus 10x, which is 0. So we know this is correct, and this would be our set of factors. Okay, so number 3, we're going to have 64p squared minus 16. So 64p squared minus 16. Now if you look at this, you know 64 is a perfect square. It's 8 times 8. And 16 is a perfect square, 4 times 4. But this one is tricky because the first step we have to do is look for the greatest common factor. And 64 and 16 are both divisible by 16, which means we can factor out the greatest common factor of 16, leaving us with 4p squared minus 1. So now when we look at 4p squared, that is a perfect square, 2p times 2p. So we bring our greatest common factor down. We're going to have 2p times 2p plus or minus, and then 1 is a perfect square. You have to remember that. 1 times 1 equals 1. So this is 1 and this is 1. And when we check it back, 2p times 2p is 4p squared. This right here is positive 2, negative 2, so that's 0. And then 1 times negative 1 is negative 1. So this is factored correctly. Okay, so number 4. 3m squared minus 48. So when we look at this problem, we know 3 is not a perfect square. So you might be tempted to throw your hands up in the air and say, nope, can't factor or done. But you have to check for your greatest common factor. And 3 and 48 share a 3. Because remember, to tell if 48 is divisible by 3, you just add up the number. So 4 plus 8 is 12. 12 is can be divided by 3. So that means our GCF is going to be 3. And we're left with m squared minus 16. Let's see, 3 to 4 one time, 18, yeah, 16. So now we can see that m squared is a perfect squared and 16 is a perfect square. So now all we have to do is finish factoring. So this is a difference of perfect squares. So we have m and m plus and minus 4 and 4. So this here is going to be our finished answer. So last one, number 5. This one's going to be a little different looking. And it's probably because we haven't seen all these different letters. So we now have a 6th power and a 4th power. Don't freak out. It's not that hard, I promise. So the first thing we have to look at is there a greatest common factor? 9x to the 6th, y to the 4th, nothing in common. Now we do know that this is a difference. So if there's not a greatest common factor, it might be a difference of perfect squares. So we're going to try setting up our factor pairs. So 9 is a perfect square. It's 3 times 3. Now believe it or not, x to the 6th is a perfect square. Because if I use my exponent properties, I can rewrite this as 9 and then x to the 3rd squared. Because x to the 6th is just x to the 3rd 2 times. So what this means is I can rewrite this as x cubed times x cubed. So anytime you have an even power, it's actually going to be a perfect square of some sort. You can rewrite it. So the same thing is true for this y to the 4th. I can rewrite y to the 4th as y squared to the 2nd. So plus or minus, and then we'd have y to the 2nd, y to the 2nd. And if we check this back, 3x cubed times y squared would be our middle term. Our bottom term would be negative 3x cubed, y squared, which is 0. So those middle terms cancel out. So even though it's kind of ugly and a little crazy, this is the correct answer. So that's how you would factor number 5. Okay, so you have to know this pattern, this difference of perfect squares. Now, the second special product is not one that we have to necessarily memorize. I've seen it before when we've been factoring. It's just the perfect square trinomial. And again, we've seen this because I've told you, remember, you can write these factors as with a power of 2. It's the same thing. So if we look at number 6, if we have x squared plus 6x plus 9. Okay, this is just a good old quadratic trinomial. So we factor it the same way we have. We start by doing our factor pairs. We have x and x. And then 9 is 1 times 9 and 3 times 3. So bottom line is, if you have a perfect square on the end, check that first. Most of the time it works out. So this goes 3, this goes 3. The signs are going to be positive because we look at the front, the second sign, and then go to the front. So we have plus and plus. And then of course always check it. 3x plus 3x is 6x. X times x is x squared. 3 times 3 is 9. So our final answer here is going to be x plus 3 squared. We typically shortcut that and write it as an exponent of 2. Now, if you choose not to, it's not wrong. Just realize that if you're looking at a multiple choice question or a multiple select question or something of that sort, most likely this is going to be the answer that shows up, this x plus 3 squared. So number 7 is going to be 49 x squared plus 14x plus 1. So again, you can sit down and you can list out all your factors. 1 times 49, 7 times 7, don't have too many here, 1 times 1. As soon as I see the fact that this and this are perfect squares, that's going to be the first set of factors I test out. So I'm going to try 7x and 7x. Both of the signs are positive. And then 1 and 1. Now if this doesn't work, then I'll try my other pairs. But usually when they're perfect squares like this, they do work out. So 7x plus 7x is 14x, which means this is my answer. So now all I need to do is rewrite it as 7x plus 1 to the second power.